Hello, welcome back. This is Math 1530 College Algebra, and we're working now on 1.7 with combinations of functions. So kind of making new functions from old functions, and we'll also worry about the domain, which are the possible values you can plug into a function. So the first thing we'll look at is the domain. Okay, and we're talking about essentially the x values as opposed to the y values. So the stuff going in. What am I allowed to put into a function? Okay, what isn't going to break the machine, so to speak? In the book, they define the domain as the largest set of real numbers such that f of x is a real number, such that f of x, which is kind of the output, the y value, is a real number. Okay. So it's always a good idea to have these working, these strict definitions in mind. But in general, there will be kind of a working definition as well that we apply to our situation. Okay. And the working definition then is the domain will be the set of all real numbers. So basically, any number you can think of will work. And then you kind of chip away at it, right? You say except when you have the following kind of following issues. So the first issue, maybe the number in the domain causes, well, it won't be in the domain if it causes this, but division by 0. Okay, so for example, if you have the function f of x equals 1 all over x minus 1. Here, x equaling 1 is bad because it causes division by 0. Okay, so that would not be included in your domain. Everything else would, just not this one particular number. Okay. The second case is when you have a negative under a radical. Okay, that causes an imaginary number. So we only work with real numbers usually. So I think maybe we have one section on imaginary numbers, but usually we will work in the real numbers. Okay, so an example of that would be something like f of x equals the square root of x plus 2, and you need to make sure that the stuff in here is what? Well, greater than or equal to 0, right? So the domain would be all real numbers that are greater than or equal to -2. Okay, so those there'll be more cases, like if you do deal with natural logs and things like that, you have to make more restrictions on the domain. But for right now, this is kind of our like I said, working definition. Okay, so let's dive in here and look at some examples that you'll be undertaking from in your homework, hopefully. So g of x equaling 2 all over x plus 5. Okay? So there's either going to be kind of the division by 0. So if you see a fraction bar, it's probably that case. If you say square root, you're going to have to worry about that stuff. So here we have a division bar. I need to make sure the denominator, x plus 5, is not equal to 0. Okay? So you set up an equation and you solve it for x. Okay? So that tells us that x cannot be -5, and we have to exclude that from our domain. Okay? So it's going to be all real numbers except -5, and we want to put that in interval notation. So on the number line, what does it look like? Well, at -5, there'll be a hole, and then everything else will be in the domain. So in interval notation, if we consider that -infinity and this the right side infinity, I'll be going from -infinity to -5. I don't include -5, so I use an open parentheses. And then I union that with -5 to infinity. And that union of intervals is the domain. So I'll just say D and then put a colon there. Okay. Okay, so that's our kind of our first example. Let's look at another one. f of x equals 3x squared minus 2x plus 5. Okay, here there's no division symbol, there's no root symbol, so therefore the domain is all real numbers. And to indicate that, we'll put negative infinity to infinity inside our parentheses. Okay, so that suggests everything works. And that'll be true for all polynomials. So you can, any polynomial you imagine, negative 2x to the 100th plus 5x to the 99th plus 2, the domain will always be all real numbers. Okay, so we like working with polynomials for that reason. They're just very well behaved with regards to domain issues. Okay, so let's look at another one, another example. And we have g of x equaling 1 all over x squared plus 4 minus 1 all over x squared minus 4. So this is getting closer to this idea of composing two functions to get a new function, or doing some sort of operation to get a new function. This first guy you can think of as 1, maybe call it f of x, and maybe this other guy is like a h of x or something. And then to get the domain, you kind of take the intersection of both of them. Okay, and we'll talk about that here in the future. But for now, all we need to do is kind of look at the denominators and set them equal to 0, and that will give us our restrictions. Okay, so x squared plus 4 equals 0. Solve for x equals, So if you try to solve, you get plus or minus square root of a negative, which is imaginary. Okay, that means there's no solutions here. There's no real number you can put in for x that's going to cause 0 in the denominator. You can put anything in there. Okay, how about the other denominator? Okay, in this case, we put the 4 on the other side. Square root property says then it's plus or minus root 4, which is the same as 2. Okay, so we have two restrictions. On the number line, if you wish, you could put it like this. There's an open dot r and open dot r, negative 2 and 2. And everything else is filled in. So we're going from negative infinity to negative 2, open parentheses union, open parentheses negative 2 to 2. So that's that middle part. And then union 2 to infinity. Okay, and that's your domain. Okay. Oops. Okay. The next one is a little unusual, and it'll make more sense once we get into. I just want to kind of get your feet wet a little bit with it. Okay. So here we have 5 all over 4 all over x minus 1. Okay, so there's kind of two parts to it. First off, there's the fraction in the denominator. There's this thing. And for that, I need to make sure that its denominator is not 0. Okay, so its denominator is x, and it'll equal 0 when x is 0. Okay, so I can't have that. Secondly, then, is this bigger denominator, right? This thing. I need to make sure that's not 0. Okay, so the part in red, I need to make sure that 4 all over x minus 1 is not 0. So I'm going to solve this equation. That guy is a rational equation, and to solve it, we multiply by the denominator to get rid of the fractions, right? So I'm going to multiply both sides by x. And on the left-hand side, you could distribute. So 4 over x times x, the x's cancel, and you get 4. Minus x times 1 is x. And then on the right-hand side, I have 0. And then solving for x, I get x is 4. So I can't let x be 0, and I can't let x be 4. So again, if you need a number line, you could draw it out, but it's just going to end up being negative infinity to 0, union with 0 to 4, union with 4 to infinity. Okay, so that one's a little harder, and we'll encounter it again when we start talking more about how we can create new functions from old functions. Because really this is kind of like two functions for the price of one. Okay, let's look at some examples with square roots. So here we have f of x is square root of x plus 2. Okay. So in this case, I need to make sure that x plus 2 is not negative. So in other words, you need to make sure it's greater than or equal to 0. Okay, so I subtract 2 from both sides. And in the end result, I'm looking, okay, here's negative 2, and I want everything greater than or equal to negative 2. So I use a square bracket, and then everything above it. So my domain will be the interval from negative 2 to infinity. Okay? And you don't have to draw out the number line. I just do that if you're still having trouble with the interval notation. I'm hoping it helps. Let's look at another example. And this is kind of another of these kind of composition type problems where we have 2 for the price of 1. There's the square root stuff, and there's a fraction bar in there. So we have the two issues simultaneously. First, we need to make sure that the stuff inside the square root is not negative, so greater than or equal to 0. In other words, x greater than or equal to negative 2. And then secondly, I need to make sure the denominator is not 0. Okay, so I find where that happens, square both sides. X plus 2 is 0. So I can't let x equal negative 2. Okay. On the number line, if you take a look at the intersection of these two intervals, so the first one I have everything greater than or equal to negative 2. And then from the second interval, it's everything except negative 2. So negative 2 is there, and it's all of this and all of this. Right, that's from the second part. And the first part is from that. Right, so the intersection is all this stuff that's in common to both intervals. And for us, okay, so nothing below negative 2 is in both. Negative 2 is not in both. It's in the first interval, but not the second. But everything above negative 2 is in both intervals. So we use a parentheses and then everything above negative 2. Okay, so domain in this case is going from negative 2 to infinity. So the point being, when you have kind of a function that's 2 for the price of 1, in other words, it's more than one function put together, you take the intersections of the bits and pieces of the domain. Okay, and I'm going to make this more clear here in a second. One more example before we get into kind of making it more rigorous. We have x square root x minus 3 all over x minus 6. Okay, so again, there's two issues at hand. We need to make sure that stuff in the radical is not negative. So we need to ensure that x is greater than or equal to 3. And then secondly, I need to make sure x minus 6 is not 0. So I need to make sure x is not equal to 6. Okay, so on the number line, and we could do this intersection type thing again if you want. It'll be everything above 3, 4, 5, 6. So 3's here, 4, 5, 6 is right here. So everything greater than or equal to 3 for the first number line, but the second number line, there's a hole in it right there at 6. And then we take the intersection. Okay, so for the intersection, the x value has to be in both. Okay, so 3 is in both. Everything below 3 is not. Okay, in both. It's in the second one, but not the first. So we're going to start at 3 and then go up to 6, but we can't include 6 because it's not in the second interval. It's in the first, but not the second. And then everything above 6 will work. So I need to write that in interval notation. So I'm starting at 3 and going to 6 with an open parentheses. I can't include 6. And then unioned with 6 to infinity. Okay, so that's the basic idea. That can get you through a lot of the homework problems. Let's take a closer look at making new functions from old functions, and this is called the algebra functions. Okay. So a lot of the topics in math are kind of just building upon earlier topics, but making them more abstract as you go along. Okay. It's kind of like art, how art works. So art kind of at the beginning of the century seems like they were trying to be realistic, right? They were trying to do realism or stuff like what was going on in Europe. And then, you know, there was more and more abstract type art afterwards, you know, later in the 40s and 50s, I guess, Jackson Pollock. Jackson Pollock must have started in the 40s, and then by the 50s or 60s, he was doing the drip paintings and that kind of stuff, which were just completely abstract, right? So anyways, it's the same kind of idea in math. The more you learn, the more abstract it becomes. And in a way, it becomes more powerful as well. But anyways, how do I make new functions from old ones? Well, you can add two old ones together. Okay, and the notation for that is f plus g of x, but it really just means f of x plus g of x. Okay, those are the same. And you can do it with plus or even minus, so I'll put a little minus in there. You can multiply them together. Okay, so the notation for that is f times g of x, but it's really just f of x times g of x. And you can, well, hold on, let's just stop there for a second. The domain of these things is the intersection of the domains of f and g. So for the domain of f, I'm going to write d with a little f there. And hopefully that's good enough, right? The domain of f. And then to get the domain of the sum, you have to intersect that with the domain of g. Okay? And same for the product. To find the domain of the product, you take the intersection of the domain of f and the domain of g. Okay. Obviously, we can also divide functions. That's kind of in these previous examples, kind of what we were doing, right? So dividing there, and again, the notation is pretty simple. That just means f of x over g of x. I don't really care which notation you use. The domain, again, is the intersection, sort of, right? So that it'll be the intersection of the domains of f and g. Okay, so if you look back at the last problem we did, the domain, you know, the top part we could, in our context, would be something like, let's call it f of x, and then the bottom part would be some other, I guess I can't say g of x, but h of x. Okay, so the domain of f of x is that first one. This is the domain of f of x. And the domain of h of x, it would have been all real numbers. Okay, so the intersection of, so the domain of h would have been negative infinity to infinity. And then the intersection of the domain of f with the domain of h would have just turned out to be the domain of f. Okay. So this is 3 to infinity, and then this would be negative infinity to negative infinity, and the intersection would just be 3 to infinity, the stuff that's in both intervals. Okay. Oops, bracket 3 to infinity. Okay, but we see that the end domain is clearly not 3 to infinity, right? There's a hole in there. So where does that hole come from? That's where g of x equals 0, and that's why the domain for this third case is different than the domain of this 2 second cases. So what you have to do is subtract away the set of all numbers where all numbers x, where g of x is equal to 0. Okay? And that's why in the previous example we don't have this number 6, because that's where well, in our case, h of x, that's where h of x equaled 0. Okay, so we kind of have to throw that one number out. And so our domain is 3 to 6 and then union 6 to infinity. Okay, okay, let's get in there and start working with some examples. Here we have a composition, or rather, we're working with 2 polynomials, so g of x and f of x. In both cases, the domain is all real numbers. The domain of G, negative infinity to infinity. And let's just maybe look at a couple of the, so let's look at it adding them, right? So if I add f of x plus g of x, I get this f plus g of x thing. That will be x minus 6 plus 5x squared. Okay? And the domain is the intersection of the domains of f of x and g of x, which is everything, right? So the domain of f of x is all real numbers. The domain of g of x is all real numbers. So the intersection of those two domains, this is the domain of f, domain of g, the intersection is all real numbers again, because every number is in both intervals. So remember, for intersection to be in the intersection, you have to be in both of the intervals, and every number is in the domain of f and the domain of g. So here the domain will be all real numbers. Okay. F times g of x is going to be x minus 6 times fx squared. And they're going to want you to multiply it out and simplify it. So distributing, get 5x cubed minus 30x squared. Again, it's the same domain of the intersections as negative infinity to infinity. So once you kind of figure out this thing here, you kind of know the domain for most of the types of resulting functions that you can create, except for that division issue. Okay, so if you have f divided by g of x, not g. In that case, then what do you have? You have x minus 6 all over 5x squared. So the domain here, just like before, negative infinity to infinity, but then you have to subtract away the numbers where 5x squared is equal to 0, because you can't have the denominator equaling 0. So where does that happen? Well, divide both sides by 5, and then take the square root on both sides. Plus or minus root 0 is plus or minus 0. Plus or minus 0 is just 0. Okay, so we have to take away 0. And the result is the negative infinity to 0 union with 0 to infinity. Okay, so to remove that, you just kind of replace it with that union symbol. Okay, let's look at a harder one, right? We don't want to send you out into the unknown without proper tools. So here's f of x equaling 3x plus 1 all over x squared minus 25. And then g of x is equal to 2x minus 4 all over x squared minus 25. Okay. So first let's get the domains of each. And for each, it seems they probably have the same domain, right? You just got to make sure this denominator here, this x squared minus 25, is not 0. So set it equal to 0. We could do a square root property on it. Square root 25 is 5. So the domain of f, which is going to also be the domain of g, is going to be negative infinity to negative 5 unioned with negative 5 to 5 unioned with 5 to infinity. Okay. And then on top of that, the intersection is also that same thing. Okay. Because every one of those numbers is in both. And you could do a number line. You could pause the video and kind of write out your number lines if you need to see that. I'm sorry, sometimes I use colons, sometimes I use equal signs. Either one is fine for me. Okay, on a test, you could write either one. So rather than writing it all out again, let's just say it's equal to the domain of f, right, which is equal to the domain of g. Okay. So for anything like f minus g of x, right, that will be the domain. The domain of f minus g will equal this negative infinity to negative 5, blah, 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 right? Okay, anyways, let's see what this thing is. And they want you to simplify it, okay? So you're going to have to, okay, so let's see what we got. 3x plus 1 all over x squared minus 25 minus 2x minus 4 all over x squared minus 25, okay? They want you to simplify these expressions. So I'm going to combine the two over the common denominator. So I have 3x plus 1 minus the other numerator, 2x minus 4, and then divided by x squared minus 25. Okay. Okay. So that then equals 3x plus 1. You have to distribute this negative, minus 2x plus 4 all over x squared minus 25. Then that will be 3x minus 2x is x, and then 1 plus 4 is 5. All over x squared minus 25. And then you could simplify that even more, right? So you have x plus 5 all over x minus 5 times x plus 5. And then you can remove the x plus 5s, and you have 1 all over x minus 5. Okay? If you look at the domain of this n thing, so let's say, for instance, you didn't know what the f and g were, and I just gave you this answer, 1 over x minus 5. You may think that the domain was all real numbers except 5. That's not true. The domain is all real numbers except 5 and negative 5. So just because you can't exactly read off that negative 5 part, it doesn't mean that it's not that it's okay to use it now. Right? So you may investigate this. You say, okay, its domain is just where x minus 5 is 0. So the only issue with the domain is that x equals 5. Okay, so you write the domain as negative infinity to 5, and then union with 5 to infinity. That would be wrong. Okay, no, it's still this domain right here. Okay, even though it doesn't look like it anymore, it's still that. So anyways, when you do your domain, you have to use kind of the original expression, or use, you have to use the domain intersections to get the answer. Okay, you don't look at that end result, the simplified result, which may have lost some of the important information along the way. Okay, so it's a very small detail, but very important. Your end result is probably not going to contain all the necessary information. Okay, let's look at the quotient of these. Right? So f divided by g of x. The domain will be the intersection, but then we're going to have to get rid of all the places where the denominator of this thing is 0. So what is this thing? Okay, so let's take a look. We got 3x plus 1 all over x squared minus 25 all over 2x minus 4 all over x squared minus 25. So for the domain, I need to throw out, in addition to 5 and negative 5, any x values that would cause that thing I just put in blue to be 0. Okay. So we would have 2x minus 4 all over x squared minus 25. I need to set that equal to 0 and solve it. Okay. So assuming x is not 5 or negative 5, we can multiply both sides by the denominator. And we end up with 2x minus 4 equals 0. And then we solve that resulting equation. Get 2x is 4, so x is 2. X cannot be 2. So now, in addition to everything else, we have the domain of f intersected with the domain of g, but we have to subtract away this number where the denominator is 0. Okay, so our domain for this quotient of functions is going to be, at the end, negative infinity to negative 5, union with negative 5 to 2, because we have to throw out 2, and then 2 to 5, and then union with 5 to infinity. Okay, so you can see there's these 3 numbers we're avoiding, and that's why we have those 3 union symbols. Okay, let's go back now and see if we can simplify this expression and see what it turns into. So to do division, all you need to do is multiply by reciprocals, right? So this is the same as 3x plus 1 over x squared minus 25 times x squared minus 25 all over 2x minus 4. Okay? And then these factors will be removed, and we have 3x plus 1 all over 2x minus 4. And again, you've lost information, right? You've lost that 5 and negative 5, but that's, you still have to, you still can't include those in your domain, okay? The result would be kind of like holes in your graph, okay? There will be a little hole there. So I'm not sure what this thing looks like. This will probably go on Desmos and look, but I'm kind of running out. I don't want to go over in time. So let's just carry on, okay? Okay, so let's look at an example with some square roots. And here we have f of x equaling square root of x minus 5, and then g of x equaling square root of 5 minus x. This one's kind of weird with regards to the domain. Okay, so let's get the domain issue out of the way before we worry about anything. So the domain of f, for that, we need to worry about x minus 5 being greater than or equal to 0, right? For radicals, you can't have negatives inside the root. So I need to make sure that x is greater than or equal to 5. Okay? On the number line, we can draw that. Here's 5, and I need everything greater than that. For the other guy, the domain of g, I need for 5 minus x to be greater than or equal to 0. So you can add x to the other side, or even, negative x greater than or equal to negative 5, and then multiply both sides by negative 1. But you have to change the direction of the inequality. Let me draw that below the other number line so we can do an intersection. Okay, so less than or equal to 5 will be this stuff. So what numbers, if any, are in both intervals for the intersection? Well, there's only one, right? It's the number 5. So the domain for f plus g, f minus g, or f times g, in other words, the domain of f intersected with the domain of g, is just going to be that one number. And we just put that in like these curly brackets. Okay? And that's kind of your domain for those first 3 or 4 types of functions. Okay, so let's actually look at maybe f times g of x and see what it looks like. So that's going to be square root of x plus 6 times the square root of x plus x. Sorry, let me look above. 5. It's x minus 5 and 5 minus x. Sorry. Okay, we can use the product rule of roots to combine this into one. And then you can FOIL out the insides there. So we have 5x, the first, the outer minus x squared, the inner minus 25, and then the last plus 5x. Okay, so that's going to be, what is that going to be? 10x. I like to put the positive one first. 10x minus 25 minus x squared. Okay. I'm just making sure that's right. 5, yeah. Okay. Okay. Let's move on to the next section. Okay. So that's one way to form new functions. Is kind of just add them together, divide them, or multiply them. Another way is to put one function inside of another. And that's kind of what happened in this example with the weird 5 over 4 over x. So you kind of, it's kind of a composition of maybe f of x equals 5 all over x minus 1. And then g of x would be 4 over x. And then to get h of x, what you're doing is putting g of x inside of h of x. Okay, so that would be 5 all over. So wherever I see x, I put 4 over x, right? And then you create this new function. And again, we're going to worry about the domains of these new functions that we create from putting one function inside of another. And of course, we call that operation the composition. Okay? So section 3, compositions of functions. And I believe we've introduced this notation before. This should be a little like open dot. F of g of x is f of g of x. You're putting g of x inside of f of x. Okay. Okay. So how does the domain work this time? First off, you need to make sure that the x values are in the domain of g of x. So x needs to be in the domain of g. Secondly, then, g of x, sort of the range of g, needs to be in the domain of f. Okay? So if g of x causes a negative under a radical, or if it causes division by 0, you need to avoid it. You need to throw it out of the domain. You need to throw out the x, which causes g of x to cause that bad issue to be thrown out of the domain. Okay, so let's first just work with maybe building some composites. Okay, so this is another example. We have f of x equals 3x minus 4, and then g of x is some sort of polynomial. Okay, so part A, they want to know f of g of x. So wherever I see x and f of x, I'm putting g of x. So it would be 3 times x, which is now x squared minus 2x plus 6, then minus 4. Okay, so this would be 3x squared minus 6x plus 18 minus 4, which is 3x squared minus 6x plus 14. Unless I screwed that up. Maybe it's screwed up in my notes. I screwed it up in my notes. Okay, this is correct. Let's try part B, which is g of f of x. And in this case, it's you're putting f of x wherever you see x in g of x. Okay, so instead of x squared, I now have 3x minus 4 squared minus 2 times 3x minus 4, and then plus 6. Okay, so first, we're going to need to FOIL out the 3x minus 4. The second part we need to distribute. Okay, so we'll have 9x squared minus 12x minus 12x, which is minus 24x, plus 16 minus 6x plus 14. Then you have 9x squared minus 30x plus 30. Okay. Some other problems, they want you to do some evaluations. So g of f of 1. Okay. So long as 1 is in the domain, you can use the simplified expression for g of f of x. So all I have to do is put 1 into that expression I just put in the box. Okay, so that would be 9 times 1 squared minus 30 times 1 plus 30. And then that's 9 times 1 minus 30 plus 30. 9 times 1 is 9. 30 minus 30 is 0. So it's just 9. Okay. Okay, the domain here, because they're both polynomials, there's no issues. The domain of f of g of x, so the domain of f of g, let's see, the domain of g we need to know. The domain of g is just all real numbers, right? So it's negative infinity to infinity. And then any of those numbers, because the domain of f is negative infinity to infinity as well. Any of the numbers in the output of G will also be in the domain of F. So the domain of F of G is just going to be negative infinity to infinity. It's basically anything goes. Okay. If that's not apparent, let's take a look at this next question, and you'll see that there's obviously some issues. Okay, so if you see a radical or a fraction bar, there's going to be issues. Otherwise, it's probably just going to be negative infinity to infinity. Okay. So in this example, the two functions f of x equals 5 all over x plus 4, and then g of x equals 1 over x. Okay. Okay, so the domain of g of x, we need to know that for this composition we're going to look at. So the composition is f of g of x. The domain of g of x will be everything except 0, right? You can't put 0 in the denominator. So it's going to be negative infinity to 0, and then union with 0 to infinity. But that's not the whole picture. We also need to make sure that anything that comes out of g of x is in the domain of f of x. Okay, so first off, let's build this composition. So wherever I see x in f of x, I'm going to put g of x. Okay, so I have 5 all over x, but in case of that, instead of x, I'm putting 1 over x, g of x, plus 4. Okay. For the domain, then, I need to make sure that this stuff is not equal to 0. Okay. And if it is, then I will have found an x in the domain of G that causes an issue in the domain of F. Okay. Okay, so let's look at it. 1 over x plus 4. I need to make sure that's not 0. That's a rational equation, so I multiply both sides by the denominator, x. I distribute here, and I get 1 plus 4x equals 0. And then solving for x, I get 4x is negative 1, and then x is negative 1/4. Okay? So I can't let x in our domain be negative 1/4 either. So I'll have to exclude that from the domain. So the domain now of f of g will be everything except 0 and negative 1/4. So I'll be going negative infinity to 0. Negative infinity to negative 1/4, right? To negative 1/4. Union with negative 1/4 to 0, and then union with 0 to infinity. Okay, now we're ready to kind of simplify it. To simplify it, you want to get rid of complex fractions. So remember from algebra, a complex fraction is where you have something like 3 over 2 plus x over 7 plus x over 5 plus x. We don't like that. Okay, so we're going to multiply top and bottom by x, and that'll get rid of that fraction in the denominator. Okay, so I'll multiply the top by x and the bottom by x. Okay, and the top I'll have 5x, and the bottom I have to distribute. Right, so I'll have x times 1 over x is 1, and then 4 times x is 4x. Okay. Okay, again, you can't necessarily see that 0 is not part of the domain if you're just looking at this end result. Okay, the simplified version has lost information. This only tells you that negative 1/4 shouldn't be in the domain. It doesn't say anything about 0. Okay, but the original, you have to go to the original expression, and this expression, you could see you can't have 0 there either, because in the denominator you would have a fraction that has 0 in the denominator, which is bad. Okay, but anyways, there's that. Let's look at one more, and then we'll move on to the last topic. So we have f of x equals square root of x, and then g of x equals x minus 3. Okay, so first, let's look at f of g of x. And let's just see what it is, right? Let's not bother with the domain yet. I'm putting g of x inside of f of x. So I have square root of x minus 3. Okay. Secondly, then the domain. So, maybe this is the first question. The second question, what is the domain? Okay, so the domain of g of x, we have to make sure that g of x works. So the domain of g of x, we could think about, that's all real numbers, because that's a polynomial. Okay, there's no division by 0, there's no square roots in that thing, so anything goes. So we're good there, domain of g. Then does the output of g of x cause anything to go bad in f of x? Okay, so we have the domain of f of g of x. Okay. So literally, f of g of x, another way to think about it is you have the square root of g of x. And then you need to make sure that this g of x thing is greater than or equal to 0, right? And of course, what is g of x? G of x is just this x minus 3. I need to make sure x minus 3 is greater than or equal to 0. Okay? In other words, I need to make sure that x is greater than or equal to 3. So those two parts put together then tells us that the domain of the composition is just x greater than or equal to 3. So the domain of f of g is going to be square bracket 3 to infinity. Okay, so it'll take a bit of getting used to, and I threw a lot at you here, but I think once you get your hands wet or your hands dirty and your feet wet, once you get in there, you're gonna figure it out. Okay, I'm hoping. If not, come my office hours and I'll work with you. All right, so the last part is on decomposing functions. So they'll give you a function and you have to identify the bits and pieces. Okay, so you want to find some function h of x which is equal to f of g of x. So maybe the idea is basically you have to find f of x and g of x. They're going to give you h of x. Okay, so examples are in order here. H of x equals the square root of 5x squared plus 3. Okay, so there's two parts to this, right? There's this kind of outer part, which I'll call the f of x. The outer part is the square root of something. So let's just put square root of x. The inner part is that 5x squared plus 3 stuff. Okay? And then you could see, okay, if I take f of g of x, in other words, if I put g of x inside of f of x, I get h of x. Okay? So instead of x, I write 5x squared plus 3. Oh yeah, that's it. Okay. All right, these are pretty easy once you get the hang of it. Let's look at another example. Let's say h of x equals 1 all over 2x plus 5. Okay. So this time, sort of the outer shape is 1 over x. And then g of x, we could say, let that be the 2x plus 5. And then we could check it. So f of g of x, plug g of x in for f of x. So I get 1 all over, wherever I see x, put 2x plus 5. One more, and then we'll look at maybe out of one Webassign problem, or my math lab. Absolute value 3x minus 4. So f of x, I'm going to say, is the outer part, the absolute value of something. And then g of x is the inner part. Sometimes they'll call that the guts, right? Okay, let's look at Webassign. If you're taking notes, you can always pause the video and write stuff down. So let's look on Webassign. It seemed like I had a problem I wanted to look at already. queued up for me. I don't know where it went. Great. Let's try number 13, see what that looks like. Okay. So let's kind of see if I can get everything in one screen here. And this guy, let's move him over. Okay, so for the functions, they give us two functions, f of x equals square root of x minus 9. Oh, this, I kind of already did this one, so let's move on to, move backwards to a different one. All right, so instead, f of x equals 2x all over x minus 5. And then g of x equals 9 all over x plus 8. Okay, so first find f plus g of x. Okay, and they kind of have the numerator for you. They just want you to figure out they have the denominator. They want you to figure out the numerator. Okay, so 2x over x minus 5 plus 9 all over x plus 8. I need a common denominator, so I have 2x all over x minus 5 times x plus 8 in top and bottom. And then plus 9, and I need to go x minus 5 in the top and bottom. I want to make the denominators look the same. And then I'm going to combine the numerators over the common denominator, and you could distribute as you go along. So 2x squared plus 16x plus 9x minus 45 all over the denominator, x minus 5 times x plus 8. And then combine stuff in the numerator, 2x squared plus 15x minus 45 over x minus 5 times x plus 8. And then we can put that into our answer. So 2x squared, and you could use the caret key for exponents instead of pushing the button. You can literally, the caret key is above the number 6, so just put shift 6 and it'll put you into the exponent so you don't have to fool around. Then 15x and then minus 45. Let's check that. Oh, what did I do? I copied down wrong. It's a 9x 25. Oh, I'm sorry. And the domain, so the issues with the domain of f is 5, the division with the domain of g is negative 8, so we have to exclude 5 and negative 8. Oh, sorry, yeah, 5 and negative 8. So the second one, you need parentheses. So f minus g of x then is 2x over x minus 5. And we need a common denominator again. So that's going to be an x plus 8. And then minus 9 over x plus 8. And this guy needs an x minus 5 in the numerator and denominator. That will be 2x squared plus 16x. And you can distribute here, but you have to be careful. You have to bring the negative along for the ride. So minus 9x plus 45 over x minus 5 times x plus 8. We get 2x squared this time plus 7x plus 45 for our numerator. Has the same domain. Okay, so let's put that guy in. 2x squared plus 7x plus 45. Okay, And then the domain is the same as before. Okay, f times g of x. So that should just be 18, the numerator is multiplied together. So 18x over x minus 5 times x plus 8. And then the domain is the same as before. Sorry, my cat's meowing at me. They must have changed the order of the answers. I was just putting in the second one. And then finally, f divided by g of x. Okay. So the domain will be exactly the same, except we have to exclude anywhere where g of x would equal 0. We'll get to that eventually. Anyways, f divided by g of x is, what is it? Well, it's 2x all over x minus 5 divided by, which is the same as multiplying by its reciprocal, x plus 8. Well, maybe I should write it in all of its glory, right? All over 9 times x plus 8. Because for the domain, we need to also now find where that part is equal to 0. So if you take that and set it equal to 0, it never will equal 0, right? You multiply both sides by x plus 8. On both sides. I had to smush that in, I'm sorry. On the left-hand side, you just get 9. On the right-hand side, you get 0. And that means no solutions. So it'll never equal 0. So the domain will be exactly the same as the domain of the first series of functions. Okay, so let's simplify this then. This will be 2x over x minus 5 times the reciprocal of the denominator. So the x plus 8 over 9. And then we can multiply that out. So you get 2x squared plus 16x all over 9x minus 45. And they have it factored in the answer. So you could probably write it factored if you want. 2x times x plus 8. Sometimes it's a little easier to leave it factored. And then the domain is exactly the same as all the other domains. So negative 8 and to negative 8, and then 5 to 5. Is that it? Yeah, okay. So those are kind of long, but important nonetheless. So get to work as soon as possible, and we'll see you next time. Okay? Thanks for watching.